In this video, I'd like to continue our discussion on functions and function notation. This time we're going to look at how this function notation can be applied in different scenarios. In this problem, number 3.6.5, this is actually a problem from Math Excel and from our textbook. We have a right triangle that has one vertex on the graph of the equation y equals x to the 8th power, and another one's at the origin, and the third is on the positive y-axis. So what we're saying here is that this point of the triangle can be anywhere along this curve. So if I wanted to create a different triangle, I would use the corner here, and I could have another triangle that's in this position, or I could have a triangle built from this position as well. Now each one of those triangles, regardless of the position of that point, will have a different area. The area will change based on the position of x and y. And so what we would like to do is we would like to express the area of the triangle as a function of x. Normally, when we talk about area of a triangle, we think of this formula, 1/2 times base times height. And while that would be fine for a geometry class, that's not really clear in terms of this particular example. Perhaps this curve, for example, represents the wall of a vessel or some sort of container, and we're trying to design a triangular component that fits inside of that, and maybe there's some rotational motion or something like that. And we've got to establish the proper sized triangular piece to fit inside of this vessel that meets some additional requirements. So this area of 1/2 times base times height just won't suffice. Now one thing that I do want to point out here is that the base of this triangle and the height of the triangle are closely related to x and y. In fact, the height of this triangle, the measurement from the origin where the triangle begins to its highest point, is simply equal to the y component. Even if we were dealing with a triangle over here in this shape, the height of that triangle would be equal to this y component, or the y coordinate. So in this formula over here, we can say that area is equal to 1/2 times the base, which we'll talk about in a second, times y. Now the height being y, now let's take a look at the base value, the base measurement of this triangle. Well, that's pretty nice. That's actually just as nice as the other one. The base, the horizontal distance, the horizontal width of this triangle is simply equal to the x component of this point. Whatever x ends up being is also going to represent our base value. So we said that the height was equal to y, the base of the triangle is equal to x. And while this equation is almost the same as the original, it's a little bit better because our objective was to write this function in terms of x, and at least now we have at least one x in the equation. The final step that we have to manage here is to take care of this y variable. While we have 1/2 times x, is there a better way to write y? What will the height of the triangle be based on the value of x? Well, since we were told that this triangle's height, this height above the x-axis, is determined by its position along this curve, well, the position, or the y component along this curve, is simply defined as the x component raised to the 8th power. So we can now say that the y component is really the same as x to the 8th power, and now we have an expression, or an equation, that describes the area of this triangle based on only one measurement, the x value. And of course we can clean this up just a little bit. We can even use function notation if we'd like. So area based on x is equal to 1/2 x to the 9th power. Or we could leave it as area and call it x to the 9th power divided by 2. We've got lots of different ways to report the final answer, but either one of these I think would be acceptable for this class or on Math Excel. Now here again, why that's so helpful for us is, let's take a look at this example. Suppose that x was equal to 2. If I were to develop a triangle that fits inside of this vessel and the x value, the width of this triangle, is 2, it would be nice to know what the area of that triangle is going to be. So again, rather than using our area equals half of base times height formula, we can use this area formula instead and simply evaluate this area formula at 2. And that ends up being 256 square units. The alternative, of course, would have been to find the base, which is 2, then the height, which is 2 to the 8th power, and then substitute into an area formula, 1/2 times 2 times whatever 2 to the 8th power is. And walking through these individual steps might be more time consuming than simply evaluating this function at the value of 2. Let's take a look at another one. For any of you that have flown in an airplane out west, you may have looked out the window and noticed portions of the plains that are irrigated, farmers that irrigate their crops. They have these traveling irrigators. And here's a picture from Google of what I'm talking about. These circles, because at the center of the circle is a pivot point, and they have these giant machines that actually rotate around that circle, spreading water on the ground. Because that machine is rotating in a circle, only portions of it receive the water and only portions of the ground turn green. And you can kind of see that in this picture here. So an algebra problem can actually be connected to that, and it's similar to what we see here. You know, perhaps this farmer has 7 of these devices all linked together, 1, 2, 3, 4, 5, 6, 7, and we would like to know how much area is covered in this particular instance based on the length of each of those irrigation tools. So as we read the problem, it says that this semicircle, whose radius is 7 times x, is inscribed in a rectangle, and the diameter of the semicircle is the length of the rectangle. We would first express the area of the rectangle as a function of x. And so in part A, I might start it this way. I know that the area of a rectangle is simply length times width. And the length of this rectangle and the width of the rectangle can easily be expressed in terms of x in this case. The length being the measurement from the center to the edge of the circle along this bottom edge can be seen up here as well. And with this 7x being a radius, we know that this length 7x and this length 7x together would make the whole width of the rectangle. So for length, I'll call this 2 times 7x, or 14x. As far as our width goes, the height of this rectangle, well, that's the same as the height of this semicircle. And again, with 7x representing a radius, whether it's measured along this diagonal or here at the vertical, that length would be 7x. And so we can say that the area of this rectangle, based on the radius of the circle, would be 98x squared. Or we can use function notation, area based on x is equal to 98x squared. Why this might be helpful for the farmer is, well, let's say the farmer has the option to buy units of this irrigation system in, say, 100-foot lengths or maybe 150-foot lengths. If each one of those x's, if each one of the irrigation components is 100 feet long or 150 feet long, they could input the values into this equation and determine how much area would be covered by the rectangle based on those irrigation components. Even though they won't water the entire rectangle, they would at least have the area associated with it, and they could determine if an irrigator of this size or this size would actually fit in their field. So in a similar exercise, we can express the perimeter of the rectangle as a function of x, and I'd like for you to try that on your own. So please pause the video now and resume playback in a moment to check your work. And there we have it. The perimeter of this rectangular plot is equal to 42 times whatever x is. So maybe this property has to be surrounded by a fence, and if they purchase the 100-foot length irrigators, well, they can substitute the number 100 into this equation and determine how much fencing would need to be purchased for that particular use. This example is pretty fun. We've got two cars that are approaching an intersection. One is 5 miles south of the intersection. So let's say we've got an intersection here, and we'll draw a real quick sketch. Say this position is 5 miles away, and that car is traveling at 30 miles per hour towards this intersection. And at the same time, the other car is 1 mile east. So we're over here just 1 mile. This is not drawn to scale, 1 mile. And this car is moving at a constant 10 miles per hour. The question that's being asked here is for us to determine the distance between these two cars based on a function of time. So you can imagine that these two distances are changing. This guy is approaching the intersection pretty quickly at 30 miles per hour. This one's approaching the intersection a little bit more slowly at 10 miles an hour. So the position of these cars is going to change, and therefore their distance between them is going to change. And we would like to find that distance based on the amount of time that passes. Well, let's remind ourselves of one thing first. The distance formula that calculates the distance between 2 points is equal to, and it's essentially a modified form of the Pythagorean equation, is equal to the difference of the x's, so x1 minus x2 squared, plus the difference of the y's, y1 minus y2 squared, and the square root of that sum. Now, this position down here was initially at the coordinate, let's say, -5, 0, because it's 5 miles south of an intersection. And this coordinate might be 1, 0, because we're 1 mile east of the intersection, and we'll assume that this intersection is the origin at 0, 0. But I don't want to use those two coordinates in their static form. I want to have some sort of equation or expression that represents this distance for each of these cars based on the amount of time that passes. So let's take this car that's moving west from east for just a second. Currently, the distance from the origin or from the intersection is 1 mile, but that distance is decreasing at a certain rate. And to indicate the distance that an object travels, we would need to multiply that rate times the amount of time that passes. This is an old formula from science class you may have seen before. So in this particular case, this vehicle's distance from the origin is 1 minus 10 miles per hour times t, the time in hours that passes. So I'm going to use that rule for our horizontal component of this triangle. And similarly, we have the other car who started at -5 units because they were 5 units below the origin. And their position is moving upward. We're increasing the position on this y-axis, if you will, at a rate of 30 miles per hour. So if we imagine x1 and y1 as our starting positions, 1 unit positive, meaning 1 unit to the right of the origin, 5 units negative, meaning 5 units below the origin, and then x2 and y2 being -10t, because that's the new position as time passes, and the new position as time passes for our other car here. Those represent our two coordinates inside the distance formula. We're going to run out of room fairly quickly here, but at least we can make the substitutions and then simplify off to the side of the screen. So with x1 and x2 being subtracted, that'll look like 1 minus 10t squared plus y1 minus y2, well, that's negative 5 plus 30t quantity squared. And while that expression, or that equation's pretty good for distance with respect to time, it's not in the format that MathXL is looking for. You can see here that they would like to simplify this into a quadratic that's been expanded. So let's go ahead and do that work over here off to the right-hand side. So all I've done here is I've expanded this. I've written the 1 minus 10t twice and the negative 5 plus 30 twice. And now we can FOIL each. And again, this was completed by using the foiling process. First, outside, inside, last for each. And now we can combine like terms. And of course, we would reorder this to enter it appropriately into the MathXL text boxes. We would enter 1000 t squared minus 320t plus 26, and these three arguments, I believe, are what MathXL would be after here. Now, using the graphing utility, we can determine the time at which the cars are closest to each other. A civil engineer might be interested in seeing when these cars will intersect, whether or not the lights on the intersection would have to be modified to continue that flow of traffic. So if we use our graphing calculator, we can graph the function and it would look something like this. Remember, we're using the letter x on the TI calculator instead of t. And the distance was decreasing, decreasing, decreasing for quite a while, and then it makes this change and it becomes increasing again. The graph switches to an increasing graph. So at this point, where the function changed from a decreasing function to an increasing function, we know we've reached a minimum, and visually we can confirm that too. And this minimum here is located at the coordinate 0.16, comma 0.632. So we have time and distance based on time. So we know that after 0.16 hours, t was measured in hours, the cars are 0.63 miles apart, which is a minimum. That's the closest distance, the smallest distance between those two cars. And I would argue that there is no danger of them striking one another at the intersection, so the lights at the intersection would likely not have to be changed. I know this video is getting quite lengthy, but let's just work through one more since the very last question is actually very similar to one of the problems we saw in the last video. So we'll go ahead and talk about this one and then call it quits for today. We have a cone that's set to fit in, we have a cylinder, that is set to fit inside of a cone. And the size of that cylinder is dependent upon the walls of the cone itself. So we can fit a tall and narrow cylinder towards the center of this cone, but if we had a cone that was just, if the cone was the same size, but the cylinder was just a little bit wider, then it would have this shape to it. It'd be a much wider cylinder, but shorter. And we can have a very narrow cylinder tucked inside, or an even wider cylinder fit down here. And each one of those cylinders is going to calculate to a different volume. So what it would be nice for us to determine at this point is what's the volume of this cylinder going to be based on x. And x is being used to establish the radius of this cylinder. So the first thing that's helpful to point out is how this hint is going to play into things. We've got a triangle that's formed here, on the cone itself. And this triangle is similar in shape to the triangle that's formed up here. So this outer triangle and this inner triangle are similar in shape. That means the ratios between the height and the width are the same. And the height of the cone is h, capital H, and the width of the cone is is capital R, and I really should call this the radius of the cone. And that ratio, height to radius ratio, is the same as the height and radius of this triangle up here. Now, as it turns out, this radius, lowercase r, and this height, I don't want to call it lowercase h because that's been defined elsewhere. Instead, we would say that this height is capital H minus lowercase h. These two ratios are equivalent. And the reason why this is helpful to consider this pair of ratios is because the volume of a cylinder is dependent upon both the radius of the cylinder and the height of the cylinder. And with this equation, we can do some manipulation to solve for lowercase r or lowercase h. And by doing so, we can rewrite the volume in terms of a single variable instead of two variables. Now I'm going to elect to solve for lowercase h here because I would like to replace h in our volume formula. We already have an idea of what radius is going to be based on x, so solving for h in this case will be more helpful. And again, since we know that r is equal to 3x, we have this h minus h up here. I'm going to ignore this middle step now. I'm going to treat these two ratios as equal to one another. And when two ratios are equal to one another, we can cross multiply and those products will be equal. So h times 3x is equal to r times h minus h. These two cross products are always equal if the fractions are equal. I can divide both sides by r and now have 3x times h divided by r is equal to capital H minus lowercase h. I could add lowercase h to both sides and then subtract this fraction to the right-hand side to see that h lowercase is equal to capital H minus the fraction 3xh over capital R. And by creating a common denominator, I can combine these two fractions. And we have h equals the fraction hr minus 3xh over r. And in case we need it, it might be worth noting that capital H is a common factor in the numerator here. And we'll say capital H times r minus 3x divided by capital R is our new value for h. Now, when we return to this volume function, volume is equal to pi r squared h. We can make two substitutions. The volume is equal to pi times 3x quantity squared, because again, the radius of the cylinder is equal to 3x. And we can make this substitution, that the height of the cylinder is equal to the fraction capital H times capital R minus 3x divided by capital R. We can simplify just a little bit here. 3x times itself is 9x squared. For right now, we won't mess with this fraction. We won't replace the capital H or capital R. And the reason for that is because the multiple choice option that you're faced with on this Math Excel question doesn't ask us to determine capital H or capital R based on a given lowercase r value. But we can rearrange this just a little bit more so that it matches the answer options available to us in Math Excel. And that would be to treat the 9, the pi, and this h, along with this capital R, as a coefficient, as a numerical coefficient in front of an expression containing x. And so with pi technically as a value pi over 1 and 9 over 1, we can actually write this expression, 9 times h times pi over r times the quantity of r minus 3x times x squared. And while this is the expression that Math Excel is looking for, this one back here would have been just as good as well. They mean essentially the same thing. As soon as we know the value of h, capital, and r, capital, we could substitute some target value of x into this expression and obtain the final volume for that cylinder. So this is a pretty challenging question. There's a lot of high-level algebra going on in here. So I'd encourage you trying your problem on your own and revisiting this video as needed for help and clarification. If you have further questions, please let me know, and I'd be happy to help. Thanks for watching.